Okay, so let's look at some questions from the problem set from lesson 2 in module 3 of the Engaged New York book. This lesson is mostly about combining like terms and expressions to simplify them, but it's about this idea of, are we really generating expressions that were equivalent to the one that we started with when we combine like terms? And the answer is yes. Two expressions are equivalent if they always evaluate to the same value, no matter what number you substitute for the variables. And in some way, we sort of take for granted that the expressions that we create when we combine like terms will be equivalent to the ones that we started with. In this problem set, what they ask you to do is combine the like terms and then substitute a given value, like here it's saying x equals 5, into the original expression you started with, evaluate it, see what value you get, and then substitute that same value for the variable in your new expression, the one you created by fully simplifying it, by combining like terms, by writing it in standard form. All these things sort of mean the same thing. And see if you get the same value. And if you do, that's sort of like their check that the value was, or that the new expression you made was equivalent. To be honest, it's not really a great check. Just to check one value and see that the two expressions come out the same isn't really a great way to see that the expressions are equivalent, but it is a quick, easy check that we can kind of sort of rely on. So let's do a couple of these. It's almost impossible to do everything they want you to do in this little space they give you, because you have to write the expression in standard form by combining all the like terms, and then make a substitution in the original, evaluate it, make a substitution into the new one, evaluate that. There's not enough room in all these. So I'm going to be doing all my work on a separate piece of paper. I encourage you to do the same. You can always show me that paper or turn it in or whatever rather than the book, but your choice. So might as well start with 1a. So 1a says, gives us the expression, I'll write it over here on this paper. 1a. 3x plus the quantity 2 minus 4x. And we want to generate an equivalent expression to this by combining all the like terms. The only like terms I see are this 3x and this negative 4x. I know you probably see it as minus 4x, but I always like to think of it as plus the negative or plus the additive inverse of the next term. So these parentheses that are containing this quantity 2 minus 4x, they're not really doing anything per se, because we're just adding these things. And yeah, honestly, I don't even know why they bothered to write these. We can essentially just get rid of them. If all you're doing is adding a quantity and there's no number looking like it's a product with the parentheses that you need to distribute, or there's no minus sign in front of it, that's different than when there's a plus sign. You gotta think about positives and negatives when that happens. But just a plus sign, we can essentially just remove those. So I'm gonna write this as 3x plus 2, and then instead of minus 4x, I'm gonna write plus negative 4x. And the only reason I have these parentheses is because I like parentheses separating my plus signs and my negative signs. And so now I can combine these two like terms, the 3x and the negative 4x. That gets me negative 1x, which I could also write as just negative x. I don't really have to have the 1 there, but because we're just starting this, I'll put the 1. And then I still got my plus 2. I can't combine the numerical term or the constant term, as some people like to call it, this 2, with any of the terms that have x's in them. They're not like. If you have terms with x's in them, you can't combine it with any other term that doesn't have an x in it. Well, when I say combine, I mean add and subtract. You can multiply and divide things. So now essentially what we're saying is that this expression that I started with is equivalent to this expression here, the one that I just made, negative 1x plus 2. And now what the book wants us to do is substitute x equals 5 in for these variables here, and then evaluate. So I get 3 times 5. Remember, the coefficient right next to the variable means to multiply, plus the quantity 2 minus 4 times 5. And so this is 15 plus 2 minus 20. the 4 times 5. And so that's 15 plus, well, 2 minus 20 is negative 18. And so when you add those two things up, you get negative 3. So this expression evaluated to negative 3 when x equals 5. That's how we would say what just happened. And now I need to check and make sure that this same expression that's supposedly equivalent also evaluates to negative 3 when x equals 5. It's not a full check that the expressions are truly equivalent, but it is sort of an okay check. So we'll do negative 1 times 5 plus 2. So I'm substituting this x equals 5 in for this x over here. And negative 1 times 5 is negative 5 plus 2 does indeed equal negative 3. So both of our expressions evaluated to negative 3 at x equals 5, or when x equals 5. Let's see here. I'm going to skip e, and I'm going to go to 1i. Okay, so that's this one right here. I'll write it over here on my separate piece of paper though. So the original expression is negative 3x minus the quantity negative 2 minus 4x. Now see, this one's different than the previous one because we just had a plus sign before the quantity in the parentheses, which allowed us to just sort of get rid of them. Here, we're subtracting this whole quantity. And if we want to get rid of these parentheses so that we can combine these two like terms, the two terms with x's in them, we have to really think about what subtracting everything inside this quantity does. And in my opinion, the best way to do that is to, instead of thinking of it as minus this quantity, let's think of it as adding the opposite of the quantity. And then there's this whole thing that the book says the opposite of a sum, that's what this negative sign here means, the opposite of this sum inside the parentheses is the sum of the opposites, meaning you could just add the opposite of every term in here. So essentially what's going to happen is this negative 2 is going to become a positive 2. This negative 4, as I like to think of it, is going to become a positive 4. Another way you can think about it is distribute the negative sign. Right? We've got this negative or this opposite sign outside the parentheses. And if we want to get rid of the parentheses, we distribute it to each term inside the parentheses. And once we've done that, we no longer need the outer parentheses and they can go away. So I'll say that this expression is equivalent to negative 3x plus, because I got this plus sign here, and then the negative 2 distributed to, this negative sign distributed to this negative 2 gives me a positive 2, and the negative sign distributed to this negative 4x gives me a positive 4x. And so then I can combine these like terms. The negative 3x and the positive 4x gets me 1x, which I'll write as just x. I don't have to have the 1 there, plus 2. So these two were pretty similar. The question 1a and 1i, they just sort of mixed up where the positive and negative signs are. And so we came out this time with x plus 2. And once again, they want us to make a substitution, x equals 5, into both expressions, and make sure that they both evaluate to the same value when we make that substitution. So I'm going to put the 5 in for this x, and the 5 in for that x, and I get negative 3 times 5 plus, I'm going to write it the way it was at the very beginning, actually, because they want us to check the original expression. And I made some changes here, distributing the negatives or whatever. So I'm going to go back to exactly how it was, actually. I'm copying it more closely from the book. So it used to say minus quantity negative 2 minus 4 times x, but I'm going to put a 5 in for that x. Okay, now I can do this. So negative 3 times 5 is negative 15 minus the quantity negative 2 minus 4 times 5 is 20. Okay, and then let me figure out what this stuff in the parentheses is, rather than trying to distribute the negative. See, this is the difference. When you're dealing with variables, I pretty much didn't have a choice. I had to distribute this negative in order to get rid of these parentheses so I could combine the like terms. I couldn't do anything until then. But when you're dealing with a strictly numerical expression, I have a choice now. I don't need to distribute this negative. I could just do the math inside the parentheses and then move on from there. So, sometimes it pays to be a little strategic and think about what you can do and what you can't. So this is going to equal negative 15 minus, let's see here, negative 2 minus 20. That's negative 22. And so what I have is negative 15 minus negative 22. That's the same as plus positive 22. And so this comes out to positive 7. And then over here, well, this is going to be really easy. If I substitute 5 in for this x right here, oh, then I get 5 plus 2, which equals 7. So both of these expressions evaluate to 7 when x equals 5. All right, let's see here. I'll jump down and do one of the ones from, actually the ones from question 2 are pretty similar to the ones from question 1. So I'm going to jump over to question 3 and do one here. How about I do E? That looks pretty complicated. So what we have, all right, 3E, 8 times 5m plus 2 times 3m. Okay, so first I want to generate an equivalent expression in standard form. So this is not in standard form because you have these products, multiple factors within each term. And standard form means, you know, all the operations are complete and all the like terms have been combined. So 8 times 5m, well, I can just do the 8 times the 5, and now I get the coefficient of m in that term is 40. So you don't have a coefficient here until this product has been resolved. And then 2 times 3 is 6, so I have 6m here, so the coefficient in this term is 6. And then I can combine those like terms and I get 46m. And now in this question, they want me to evaluate both of these when m equals negative 2. Sorry, I just realized I'm off the screen a little bit. And then make sure that they both evaluate to the same value. So I'm going to substitute m equals negative 2 in for this m and that m, and I get 8 times 5 times negative 2. So it looks a little different the way I had to write it, but I just didn't want a negative sign up next to my multiplication dot, but I'm just doing 5 times this value, plus 2 times 3 times negative 2. Okay, so I'll do the inner multiplications first. It actually doesn't matter. You could pretty much work in any direction you want as long as you do this addition last. But I'll do the ones on the inside. So this is 8 times 5 times negative 2 is negative 10, plus 2 times, let's see here, 3 times negative 2 is negative 6. And so 8 times negative 2 is negative 80, and 2 times negative 6 is negative 12. And when I add these two things up, I get negative 92. And then over here, this is going to be a lot easier. I'm just going to substitute negative 2 in for this m. So I get 46 times negative 2 equals negative 92, just like I got over here. Notice that this side is much simpler to do. That's kind of sort of why we call it simplifying an expression, when we take this big old expanded thing and just write it in standard form as 46m. We say it's fully simplified, or we call this simplifying an expression. And I think you can see why pretty easily, right? Okay, let me do one from the question 4 category. How about, we'll do E again. So 4E says 56k, am I on the screen okay? Nope, I'm too low. 56k divided by 2k, and that's it. That's actually the whole, that's the whole expression they want us to do. Okay, so this one's a little weird. It's a little different from the rest of them because this is the first time where we're going to do an operation that's not addition or subtraction with the variable. See, if this were just 56k divided by 2, then we would just divide the coefficients, 56 and 2, and we'd be left with 28k. But they want us to divide by k as well. Well, k divided by k is just like any other number. When you divide it by itself, you get 1. And so what's essentially going to happen here is I'm going to divide the 56 by the 2, and I get 28. And I'll divide the k by the k, and I get 1. Well, 28 times 1 is 28. If you're not sure why I can do it that way, sometimes it's easier to see things with numbers. So I'm going to grab a different colored pen. I want you to know that this is separate from what I'm doing. Let's imagine this was 56 times, well, actually, essentially what I'm doing is I'm going to show you why this works using the value they want me to substitute into the expression to check for equivalency. I'm going to do that, and at the same time I'm going to sort of explain why the move that I made works. So they want me to substitute k equals 3. So let me use the 3 in my explanation. So this is 56 times 3 divided by 2 times 3. Well, one way you could think about it is the fact that we know that division is the same as multiplying by the reciprocal or multiplying by the multiplicative inverse, or in other words, what we call in the class lots of times a keep, change, flip. So I could write this as 56 times 3 divided by 3 times 2. Like, I'm allowed to switch these back and forth. That's a commutative property. Then I'm going to change this to multiplication, and I'm going to write the reciprocal of both these numbers. The reason I'm doing both is because 3 times 2 is really actually 6, right? And the reciprocal of that would be 1/6. And if you do 1/3 times 1/2, you get 1/6. And so now, see how now I can do these multiplications in any order I want, 56 times 3 times 1/3 times 2. And if I do the 3 times 1/3, I wind up with 1, and I still have my 1/2. And then 56 times 1/2 is 28. So this all came out to 28 just like it did before. In fact, it didn't really matter what number I chose for k here. I could have gone through the same process or any other process you wanted, and it would have always came out to 28, because the fact that the k's got sort of divided out, as some people would say, now it doesn't matter what value you put in for k. This expression is always going to just equal the number 28. Try any value you want. I could go, this time I'm going to substitute, I don't know, let's just make it easy on ourselves. I'll do 2 this time. 56 times 2 divided by 2 times 2. So I put a 2 where both these k's are this time. And this time, instead of going through this process of multiplying by the reciprocal and keep, change, flip, let's just do it the easier way. Let's just do 56 times 2 is 112, divided by 2 times 2 is 4, and I'm pretty confident that 112 divided by 4 is 28. So yeah, when you have two terms and they're being divided and they have the same variable, and as long as there's no exponents up here, which, that's not a 0, I'm drawing like a circle to point out where an exponent would be if there were an exponent. As long as there's no exponents up here that you need to worry about, and we can talk about that later, then they essentially just cancel out and you're left with numerical terms. All right, do I want to do any more for you? Yeah, I'll do 1 from 5, and then I'm done. All right, so 5, I'm gonna go back to blue. I like it better in this purple. 5, I guess we might as well just keep sticking with the E's, because the A ones are really easy. So I feel like if you watch me do the E one, you should be able to go back and do the A one kind of easy. So 5E says, find the result when 13V plus 2 is subtracted from 11 plus 5V. So to subtract something from something else means that's the thing that's being subtracted. Oops, I wrote this wrong.